Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc in the University of Helsinki over in Finland. And I study cosmology. So that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, all of the cool things happening inside the universe. I love being a cosmologist, I love being a physicist, and I love chatting to people about all of the cool things happening inside the universe. And that is the purpose of Cup of Cosmology, where you can ask all your questions, and I will do my best to answer, but I guarantee I will not have all the answers to all of your questions, but we're going to try. So hello to all of the regulars. Hey, David Dunn, David Howden, Scott, Ange. Great to see everybody. Welcome. So first up, a bit of housekeeping. I have a new webcam and a new microphone today. So please do let me know if there's any issues. Let me know on video and audio quality. I assume everyone can hear me, or you already would have told me. Let me know if it's loud enough, if the camera's good. Testing a new setup today. So there might be some technical gremlins, but let's see what happens. Hopefully this is going to be a fancier new setup that will reduce the previous sound issues that I had. I know my old microphone sometimes had a metallic sound to it and occasionally cut out. So hopefully the new one will be nicer. And I think I've got rid of the annoying autofocus on this new camera. So hopefully things are going to go smoothly. And as we're doing housekeeping, if you haven't subscribed to the YouTube channel, please do so. I'm almost at 300 subscribers. Leave a comment, like the video, all of the usual things. YouTube does boost all of the engagement. So it's really appreciated when anybody does all of the right YouTube buttons, press the things, make stuff happen. Really appreciate it. Good comment, sounds good, looks good, awesome. Thanks for letting me know. Let's see how stable it is. Should be a pretty new fancy webcam mic combo. So hopefully it's going to be an upgrade from what I had before. So good to know that you can hear me and see me without any issues. So yeah, I'm a theoretical physicist. I study the universe, which is one of the coolest things you can study, in my opinion. It's amazing. I love studying the universe. And I love chatting about everything inside the universe, everything from, the Big Bang until today, or from the end of inflation until today, and everything that we can study in between. It's really fun. I don't have a topic prepared today. I have lot of stuff going on and I just couldn't be bothered, to be honest. It's quite difficult every week to come up with a new topic, but anytime I don't have a topic, you will come up with amazing questions. So the idea today, and as often in Cup of Cosmology, this isn't Ask Me Anything. The idea is that you people can ask me anything you want about the universe, about cosmology, about physics, about being a scientist, about Finland, about academia, if you want to get me to rant. About fun song combinations, that if you put two songs together, you get fun medleys. Please don't make me sing. So anyway, this is an Ask Me Anything. You people can ask me anything you want. That's how an Ask Me Anything works. So last week, I dumped a bunch of stuff on you. It was a very in-depth review of some of the cool things happening in the universe and some of the open questions we have, like what is dark matter? What is dark energy? What's going on with lithium? And I left a lot of open questions. If you ask me some of the biggest questions, like what is time? I'm probably not going to be able to answer, but it's always fun to chat about those things. So what is the hoodie? This is my Quasistar hoodie. So Quasistar is my second favorite YouTube channel after Cup of Cosmology, of course. They do amazing science outreach with really cool animations. And the hoodie is ridiculously cozy. So this is my Quasistar hoodie. But yes, it is a very, very cozy hoodie. Quasistars, what's up with those? I'm not completely sure what you mean by a quasistar here, Scott. So on that note, let me just mention that I'm trying to get somebody back on the show, or somebody on the show, to talk about baby stars and how we go from gas clouds to stars. And I think it could be a really cool topic, like how stars are formed. Still pending, but maybe that's going to happen at some point in the next few months, so hopefully. So a star is basically a big chunk of hydrogen and helium that you put in the same place with the right amount of pressure, and it can collapse to form a star. And then you have a battle of the pressure pushing things outwards and gravity pulling things inwards. It's very high temperature, high density, high enough temperature and density that you can ignite stellar fission. You stellar fusion. You fuse elements together to make heavier elements and release a lot of radiation. In the meantime, a lot of light, which is why we see stars glowing. So basically a big giant ball of fire, and we see the light. So quasi-stars are things that are almost stars, but not quite stars. So they have some of the properties, but they're missing one of the properties to actually be a star. I'm not completely sure which one, but they're not a complete star. On that note, you can have things that are failed stars, like Jupiter. If Jupiter were 10% more massive, it would be a second star. We'd have a second star in the solar system, which would mess everything up and would be a bit funky. But if Jupiter were 10% more massive, it could actually be a star. So Jupiter, some people might describe as a failed star. It's like brown dwarfs. They're stars that are almost stars, but kind of fail and don't actually make it into the full stellar ignition process. So that's my understanding of quasi-star, something that wants to be a star, but isn't quite a star. What's your opinion on ChatGPT and AI in general? I feel like this is a question that we had 2 weeks ago, or last week even, when I ranted about ChatGPT. I'm not a fan of ChatGPT. It's a glorified auto text predictor. It's it's very good at saying a lot of nonsense. I think artificial intelligence could be very good. There's a lot of potential applications. I don't think we need to worry about it taking over the world anytime soon or replacing most of our jobs. I think machine learning, I'm much more skeptical of. Artificial intelligence is great. There's a lot we could do. We very much need to consider the ethics of what we're doing as well. But there are some very cool applications to artificial intelligence, to machine learning, to ChatGPT. But I'm not on board with all of the hype. I think it's a cool curiosity. It's something that is in its infancy and still requires some developing before I'm going to get hyped up about it. I know some people are gradually trying to use it more and more in Astro and Cosmo with various degrees of success, and that's cool. It's great to find ways to optimize our processes, but I would always be skeptical of what machine learning or artificial intelligence spits out. It's not completely foolproof. It's very far from being foolproof. So this is my diplomatic answer to the question, but I'm definitely not a fan of ChatGPT. And I am very, very, very much not a fan of using AI to make art, because you're basically stealing from artists. This is something that should not be done properly. It should be regulated and controlled, and I don't think art done by artificial intelligence is actually art. But moving aside from the rant, Quasistellar objects. Yeah, I'm not really sure much more about quasistellar objects. It's really not something I've worked on. But it's not something I've worked on. So my hand wavy answer that I gave is as far as I can go. Might have to respectfully disagree with a couple of those things, but only because I just watched a bunch of Quasistar videos. Yeah. I think, artificial intelligence can have a lot of applications. There's a lot of cool things you can do with it. I'm just very skeptical right now of a lot of things about artificial intelligence and machine learning in general. But I'm sure, there's a lot of great people working on this and they're going to iron it out. So there's a lot of cool stuff that can be done with artificial intelligence and machine learning, and it is where we're headed. It is the next technological revolution, I think. But I'm very suspicious of ChatGPT. I do not trust, and I refuse to use it. I do not trust anything that it spits out. And you can tell that it's spitting out nonsense. But it's like if you ask it to tell you a joke, it will fail spectacularly at it. It's just got a big data set of text, and it's trained on this data set, and it's very good at pretending to know what it's saying without actually saying anything. Kind of like politicians or the people at conferences who have comments instead of questions, who just like to make themselves sound smart. Yes, I know this is a topic I can rant about a lot, so let's leave it at that. Have a nerd's night for you. What would it be like to live in a universe with 2 time dimensions? Oh no, that's fun. That's very curious. I've never considered a second time dimension. So we're used to 3 spatial dimensions, right? We can go in, out, left, right, up, down. And we have 1 time dimension. We go forward in time. We can never go back in time yet. Probably never. So what would it look like to have 2 time dimensions? I'm not completely sure. I guess then you could have another, like you could move forward in time and left, right in time, which doesn't really make sense. Like you could sidestep away from one timeline to look at it. It's a very cool sci-fi idea, but I'm not sure how it would actually look in reality. It's something I've actually never thought about. I think the problem here is that the way we define time as being the movement between kind of one state and the next state, what would it mean to have another time, a second time, running parallel, perpendicular to the first time? Would it form an independent coordinate? That's very curious. I have no idea what that would look like. But that's absolutely something that I'm going to ask my colleagues if anyone's ever thought about it, because I feel like that's going to be a fun discussion. But I have no idea what you would do with 2 time dimensions. It would make the universe very funky. You'd probably end up with some random paradoxes. So it's something. Could you? Yeah, it's like going sideways in time. It's odd. It's definitely odd. Jupiter would need about 90 times its current mass to qualify as a red dwarf. Yeah, I mean, I said 10 times, it's order 10. It's okay, 90 is closer to order 100. 1 order of magnitude. What's 1 order of magnitude between friends? Yes, 90 times its current mass, Jupiter would be a star. I think the 10% number actually comes from Stargate, which is obviously not an accurate source of knowledge, at least not scientifically accurate knowledge. So yes, 90 times its current mass sounds more believable. 90 times its current mass, yes. Okay, I'm jumping about in the questions here. Real stupidity beats artificial intelligence every time. Yes, and artificial stupidity beats human stupidity every time. Okay, read that comment. Okay, another one on ChatGPT. I think the way it creates plausible seeming but fictitious citations shows how little intelligence it really shows. Yes, if you ask it to find you citations from famous authors on a topic, it will produce nonsense papers that sound plausible. Like, here's a title that these people might write, here's a list of reasonable sounding authors, and the papers don't actually exist. So it is very good at producing nonsense bullshit answers. That is a reason. Never trust anything that you read from ChatGPT. Always fact check it. It is the epitome of fake news. Do not trust anything on ChatGPT. Just in general. Yes, I keep saying moving on and then coming back to it. Heinen had a story with 3 time dimensions. Cool. I will have to read that, because that does sound really, really cool, actually. Heard about it in a throwaway quip by a Minute Physics, and I keep going back to that thought experiment. It is a very cool thought experiment, and one I definitely want to discuss with other people, because I think you could end up with some fun quirks there. On that note, in a couple of weeks, we're going to be doing a cup of cosmology with 2 people from my office. And it's going to be a lot of messing about and laughing. And the topic is going to be fun and creativity. Fun and creativity with general relativity. We're not calling it that, but basically we're going to tell you about all of the cool things that happen in general relativity, like time dilation, length contraction, twin paradox, stuff like that. So we're going to be talking about all the fun stuff of general relativity, 26th of February. Quasistars are theoretical early universe stars that could be many times larger than possible today. Okay, so I will definitely have to look into quasistars before I can answer that more, because I clearly have not caught up with my quasistar knowledge. Question from James a while ago. What gives waves its momentum? At a quantum level, can we see a wave? This is a great question. And we know that particles behave as a wave. We can see at the quantum level, every particle has both particle and wave nature. And this is something we can prove. We can see that the behavior of particles sometimes acts as wave and sometimes as particles, like electrons, photons, particles of light. They will sometimes move as particles or sometimes as waves. So this is something we can see. But then you're asking if you can see the waves themselves. I'm not sure exactly what you want to see here. Like, an electromagnetic wave is a wave, but it's not something we can directly see. A sound wave is not something we can directly see, but a pressure wave is something we can see. This is something, if you've seen the typical images of the Concorde hitting supersonic speed, and you get that nice cloud coming out of it. And that's a wave, that's a shock wave that it's producing. So we can see some waves. As to what gives a wave its momentum, well, that depends on what it's a wave of. Every wave will have energy, and that energy has momentum. For an example, if we're talking about a photon behaving as a wave, the photon has an intrinsic energy based on its motion. Other things have an intrinsic energy based on their mass. So waves will have momentum based on the fact that they have energy. And can we see a wave? It depends what type of wave you're talking about. We can see the effects of an electromagnetic wave very easily. You could argue anytime we're looking at light, we're actually seeing an electromagnetic wave. So I think some ways we can see, some we can't. It depends. Like a gravitational wave, we cannot directly see with our eyes, but we have been able to measure gravitational waves, which is one of the coolest things. The fact that we've actually been able to measure gravitational waves. I will never get over how amazing it is that humans decided to build a system of lasers bouncing back and forth across mirrors to measure tiny, tiny, tiny differences in distance of the order of 1 part in 10 to the 21, which is like a billionth the width of a human hair. And we measured this with lasers. It's ridiculous. I'll never get over it. And if that's not cool enough, we're going to do this in space in 10, 15 years. Yeah, gravitational waves are amazing. I know no one asked about gravitational waves, but waves in general, and my mind jumped. Okay, I know I'm jumping about through the comments today, so there's a higher chance of me actually missing comments today. Yeah, no need to apologize, Scott. As always, I appreciate the questions, and Quasistars is definitely a fun topic and something I will absolutely come back to. I'm actually going to make a note of that because I always say I'll make a note of that and then never do. But Quasistars is something, maybe I can get one of the space physics people in my building to talk about Quasistars, because that's absolutely not my topic. Example question, have we seen a photon? Yes, there's actually, so I was the teaching assistant. Yeah, okay, just seeing comments, aka LIGO, aka LISA, because I didn't actually mention the experiment names. Yes, we had LIGO. It's the ground-based one that measured gravitational waves. LISA is the one we're going to launch to space to measure gravitational waves. Amazing, amazing missions. Okay, so have we seen a photon? So missed a bit. When is that relativity stream again? 26th of February. So 4 weeks from now. It was either next week or in 4 weeks, and we all decided in 4 weeks. 26th of February, Sunday. Both of the people on the stream are people who have already been on Cup of Cosmology, and now I'm getting them together. And it's going to be fun. We have a lot of ideas going around. For now, we're stuck on the title because I'm refusing to call it creativity and relativity. So we'll see. Maybe I give in and go with that funny title. Anyway, have we seen a photon? So there was I was a teaching assistant on quantum mechanics, on Introduction to Quantum Physics this last period from, I'm talking quickly, from November, December. It's an 8-week course, Introduction to Quantum Physics, and I was a teaching assistant. So it's an introduction to all of the cool and quirky stuff that happens in the quantum world. There's a lot to cover. It's really fun. I really enjoyed being the teaching assistant on that course. It was a lot of fun for a lot of reasons. And there was one exercise that we set the students in the first week, which was to calculate if your eyes are capable of detecting a single photon or if you need a stream of photons. And once you did the calculation, you basically found that your eye can activate with as little as like 3 or 4 or a handful of photons. Just a few photons is enough for you to actually measure it. So our eyes cannot pick out one photon, but a couple of photons, like 5, I think it was, or with a 5 to 10, and your eye can already pick out these photons. So have we seen a photon individually? We can do experiments where we do see a stream of photons. We know our eyes are sensitive to order few photons, and I think there's a fog that is sensitive to individual photons, some random fog. But that tangent aside, we can actually play about with individual photons. So you can't really see it directly as like, look, this is a particle, because once you observe it, its momentum is indeterminate, and if you get its position, you don't have its momentum, and vice versa. So it's quite hard to point to something, say there is a photon, there is a particle, because particles kind of blurry, smudgy mess everywhere. Quantum physics is fun. My mind is jumping about a lot, so if anything I say is not clear, please do ask me again, and we can recap and go through it again, because I know I'm jumping about and maybe explanations are not as clear as they should be today. Let me just go through the comments again. I know there is a comment that I missed from Ben that I will go back to. LIGO, LISA, even though sound travels relatively slow through our atmosphere, it's still amazing that we have airplanes that can go faster. Yeah, the Concorde planes were amazing. I never got to see or hear one, but it's amazing that we had these planes that could actually, breach the sonic barrier and make a loud boom. It's very cool that we had these planes at some point. If they ever make a supersonic submarine, I'll be really impressed. Yeah, that would be weird because sound in water travels very... Yeah, let's not mess about with submarines too much. Deep breath. Yes, deep breath. I think there are frogs that are known to be able to detect individual photons. Yes, exactly. We linked to the article about the frogs in this exercise, and it was really fun. It was a fun exercise to do, and it was it was a really fun exercise to get the students to calculate if we were sensitive to single photons. And when I got the exercise first before getting the solution, and I was staring at it like, okay. So then I solved it myself. I was like, no, I don't believe my result. And then got the actual solution. Was like, huh, that's pretty cool. So it's fun. Whew. Sound in water is even faster than it is in air. Yes, because there's more friction with the water, so it's more dense, so sound waves can travel easy. Yes, makes sense. Okay, let me just go back to the question that I missed from Ben. Do you think the theory that space-time is a result of entanglement is plausible? I'm not sure. See, the problem here is that space-time is a concept that is intrinsic to general relativity and to how we understand gravity. Einstein's general relativity in a nutshell tells us that objects with mass bend space-time, and this bending of space-time tells objects how to move. So space-time is an intrinsic part of general relativity, which is a great theory for explaining large things like why we stay in orbit around the sun, the motion of planets, and how everything behaves, and how gravity actually works. At least we have a pretty good understanding. Now, entanglement is something that happens in the quantum world. It's when you can prepare particles with opposite spin or with opposite quantum properties, and they are intrinsically linked so that when you measure one, you collapse a wave function of both, and then just by measuring one, both states are determined. Did a whole stream about entanglement. I'll link to it. I always say I'll link to it and never do, but I'll link to it. Or you just search on Cup of Cosmology entanglement and you'll find it. So the problem here is that we don't actually have a theory of quantum gravity. We don't know how to put the tiny, tiny, tiny quantum world with general relativity. And the biggest problem here, or one of the biggest problems, is that general relativity is extremely predictive. You do an action, you know what's going to happen. You put energy into a system, you're going to curve space-time. Curvature of space-time is going to tell an object how to move. You can calculate it, you can predict it. From initial conditions, you know the final state. In quantum physics, there is a level of knowledge that we don't have and that we can't have. There is a level of randomness in quantum physics. You can prepare electrons and you measure it, and there's a 50% chance of it being spin up or 50% of it being spin down if you've not done anything to the system beforehand. And, if it's completely randomly prepared electron. So there is always randomness in quantum physics. And trying to match the randomness of quantum physics with the very clearly determinate outcome of general relativity is extremely difficult. And we haven't been able to do it yet. We're not sure how to knit these two things together. So the question was, do you think the theory that space-time is a result of entanglement is plausible? I'm not sure. I don't think anyone can really make that claim because that would require understanding entanglement at the level of space-time, which are just concepts that are really difficult to join in any meaningful way. So I actually have not read this theory myself. I'm not sure what theory exactly you're referring to, but a priori, I would say it sounds a bit difficult to put these concepts together. So if someone claims that they've done it, I'd be very interested to see how, because it's extremely difficult concepts. That is way too hot. Just forgot that my tea was not cool, and now that was way too hot. I have a problem with hot drinks. My tea was made 30 minutes ago, and I still cannot drink it. I make tea like half an hour, 45 minutes before I actually want it, because you just saw 30 minutes after making tea, and now my tongue is hurting because tea is too hot. Anyway, catching up with the comments, because I just spent a while on that one and I need to catch up. Deep breath, yes, I keep seeing the deep breath comments, like, yes, I need frequent reminders of that. The Dwarf got to that one. Sound goes even faster through solids, yes. So what's the speed of sound in neutron star matter? I have no idea what the speed of sound is in a neutron star. So a neutron star is the densest object, one of the densest objects that we know of in the universe. they're so dense, there's so much energy packed in there that you can actually fuse protons and electrons together, which is something that shouldn't happen. But you can push everything together so much that you end up with a neutron star. We're not completely sure what's happening inside neutron stars. There's a lot of people working on that, and you can relate this to holography somehow. Weird, random stuff that people I know work on topics connecting these things. So I have no idea what the speed of sound is in a neutron star, but that's something we could calculate. I think for the speed of sound, you basically just need the density of the object. So yeah, that's something that one could calculate. Not this one, but one could calculate this. Yeah, your tea is too cool after 7 minutes. Then you have very good tolerance to heat. My tea is still too hot. It was made at 90 degrees because it's chamomile. It's about 95-ish degrees, so it's just under 100 because it's chamomile. That's what it needs. But yes, it was hot when it was made. It's still hot. My tea will be drinkable by the end of the stream. We have coffee breaks in the office, and sometimes I go in with tea and then just sit there staring at my mug, and at some point it's like, I'm just going to take this back to my office because yes. Yeah, tea. Oh, great. Lukewarm. No, you brew my tea hot, but by the time I drink it, it needs to be lukewarm. Like, make sure you brew it at the right temperature. I have opinions about this, but by the time I drink it, it needs to be drinkable, and I can't drink hot things. Yeah, I'm always the last person to finish my coffee or my tea when anywhere. So I've got in the habit now of actually getting either tea or coffee with food, so that then it's actually cold by the time I finish food. Yes, random topic change there. Underwater sonic booms would be absolutely devastating to sonar and all the fish that communicate through clicks. Yes, a lot of fish use sonar. Whales, for an example, use sonar. Any type of sonic boom under the water would be very damaging to any type of wildlife or ecosystem, and that's obviously something that we want to avoid. More comments here about tea. I need a vacuum chamber to boil my tea in low pressure, low boiling point. Yeah. No, I think the way the tea's prepared is fine. It's just that I have very low tolerance to hot drinks. So, like, at some point I was drinking mate, which is supposed to be drunk really hot, and I burnt myself every time I tried it. Yeah. Food I'm okay with, but drinks I will burn myself constantly. You know, on a semi-related note, YouTube, if I don't tell YouTube the chapters of my videos, it tries to do it automatically, and it kind of pulls out sentences from the videos and sets them as chapters. And I was looking at a stream that I did some months ago, a couple of weeks ago. I was looking at the stream, and I was just curious of what chapters YouTube had given. And there were reasonable chapters, like, what is the CMB, dark matter. And there was a chapter that had the title, Cucumber Tea is a Singularity. And I was staring at this like, what's on earth? And I clicked on it, and indeed that chapter starts with me saying, yeah, cucumber tea is a singularity. So tea conversations are not new on this show. But yes, there are shrimps that hunt by creating sonic booms. That is fascinating. That is really, really cool. I did not know that there are shrimps that hunt by creating sonic booms. Nature is absolutely amazing. There are so many random animals and things out there, like random animals and plants and fungus. It's amazing. We live in this world with these incredible species. There are fish that see more colors than we can ever see. Apparently, there are shrimp that hunt with sonic booms. I'm making a note of this because I'm going to go down a rabbit hole later about that. That sounds absolutely amazing. Yeah, there are so many random and cool things in the universe. It's amazing that we get to share this planet with so many incredible species. Amazing. Hey, Abyss, great to see you. Haven't seen you in a while. Really nice to have you here, Abyss. You missed our discussion about artificial intelligence and how I do not like artificial intelligence and how I do not like ChatGPT. Mantis shrimp, basically, they punch so hard it makes sonic booms. That is cool. That is cool. I'm going to do a deep dive on that. So there was a question that I missed at some point, an actual physics question, and not a question about my tea. Question from James. Topic in your mind? Perfect. I like questions about photons and particles and stuff. Are photons affected by temperature? Is its speed never affected? Okay, excellent question. So you can slow a photon down by making it travel through something that is not air. Sorry, that is not vacuum. Light travels through. You're against AI too. Excellent. Wise choice. I'm not against it fundamentally, I just have concerns. I'm just asking valid questions about artificial intelligence. Well, I'm not asking them, I'm just staying away and letting other people ask the questions. Okay, those are pistol shrimps. They can create cavitations due to their fast speed. They also have 16 light detection cones. Why do shrimp need to see so many colors? What's so colorful at the bottom of the ocean? Why do they need so many colors that we can't have access to? I want to be able to see more colors. It would be so fun to see more colors. Anyway, there was a question. There's a lot of comments about mantis shrimp. I appreciate the shrimp thing here. This is very cool. I am absolutely going to read up about that. But I was talking about photons and slowing them down. I'm just looking for the question again because I got distracted. Okay, so you can slow a photon down or a particle of light down by making it travel through different mediums. A photon will not travel through lead, for example. It slows down too much. Photons will not travel slower in water than they do in air, and they travel slower in air than they do in vacuum. So you can slow a photon down. But as for temperature, you can relate the temperature of the photons more or less to their energy. So when we talk about the temperature of the photons, what we're mainly talking about is their wavelength, which we then convert, to an energy. And the wavelength is something that we can change. If you have a particle of light, a photon, every photon has a wave associated to it, and this wave is going to have a wavelength, Slinky's back. And this wavelength can be stretched or compressed. This is something that we know happens. As light is traveling through the universe, it's going to be compressed slightly, and as it travels away from you, it's going to be stretched. But also as the universe is expanding, this is also going to be stretched. So we can have changes in energy of photons and therefore in the wavelength. But the temperature itself is not so much what we normally talk about. So we have the electromagnetic spectrum. On one side, we have very small wavelengths, very high energy, where we have gamma rays. On the other side, we have very large wavelengths, which corresponds to lower energies, where we have radio waves. And we can absolutely change the wavelength and therefore the energy of these things. Gamma ray photons can travel through light years of lead. Yeah, so the higher the smaller the wavelength, therefore the higher the energy, the harder it is to slow a photon down. So if it changes from a vacuum to lead, that transition is going to take a bit longer for it to slow down because of the different wavelengths. So if you wait long enough at some point, yes, a photon can eventually travel through different sources, but it's going to travel a lot slower in mediums that are not a vacuum. And the more dense the material is, or the more compact the material is, the harder it is for the photon to propagate. So we can affect the wavelength of photons, we can affect the energy of photons, and we can affect how fast it travels through material. So these are things that can happen, these are things that can be changed. But once you know the approximate wavelength of a photon, you can also calculate its momentum, and then depending on how things are emitted, you can get an idea of the temperature, but the temperature will mainly depend on the type of energy source. Okay, let's see, more questions. Yes, back to pistol shrimps with 16 light cones. Is my tea drinkable yet? Tea is now at perfect temperature, and in 3 minutes tea will be cold. So I have like a 3-minute window where tea is good. Yeah, I'm very particular with my tea. According to one source, oh, that's not a good start. According to one source, hopefully more sources. According to one source, the speed of sound in a neutron star starts to appreciate a fair fraction the speed of light. Nice. So I wanted to, or someone could calculate this. I will trust the source that David's found here. So apparently in a neutron star, the speed of sound approaches the speed of light. That is very cool. And it makes sense given how dense it is. You missed the interesting part of the discussion, AI and language models. Yeah, more than a discussion, it was me ranting, but it was fun nonetheless. So on the topic of gamma rays are easily scattered due to their high frequencies. Lower frequency photons and neutrinos can permeate through dense objects. Yes, it was opposite way around. Yes, thank you for correcting me on that, Abyss. Yes. When they have a very small wavelength, it's easier for them to be stopped. When they have a broader wavelength, it's harder for them to be stopped. Yes, that makes sense. Thank you for that. Yes, flipped it around. No, that makes sense. Okay, So, on the topic of temperature and photons, I was saying that the temperature of photons depends a bit on the source and the type of emission. For an example, if an object is emitting as a black body, it means it emits at all frequencies. And we know the properties of black body, we know what is emitting at all frequencies, so we can calibrate the temperature. And now, the best a black body is just something that emits at all possible frequencies. So it doesn't emit light at one frequency, but across the whole spectrum. And the most precise and perfect black body that we have ever been able to find is the CMB, the cosmic microwave background radiation. This is the most perfect black body we've ever been able to find. It emits at all frequencies. If we take the spectrum of this, like what frequencies are emitted from the CMB, it covers all frequencies. It is the most perfect black body we have found. However, all of the photons here are at a specific wavelength, which is in the microwave range of the electromagnetic spectrum, which is why this is the cosmic microwave background radiation. But we know the temperature of the CMB. The CMB is at 2.73 degree Kelvin, which is minus 270 degrees Celsius and minus 440 degrees Fahrenheit. We know this, we can calculate the temperature of the CMB, and it's very cool that we have the temperature. Yeah, who had 36 minutes on their bingo card today? It's 36 minutes today. Yes, so CMB, cosmic microwave background radiation, all this light we can see in the universe, afterglow of the Big Bang, gives us a whole amount of information, and it is also the most perfect black body that we have. And we can calculate its temperature, which is 2.73 degree Kelvin, and we know its wavelength is in the microwave range. As the universe gradually expands, this is going to stretch more and more and shift out of the microwave range and into the radio range. In a couple 100,000 years, if people measure the CMB, they would have to measure it with a radio telescope and not with a microwave one. So that's just a random excuse to throw up the CMB. I realized we were at 36 minutes and I hadn't shown the CMB yet. So I just needed a random excuse, and we were talking about temperature and photons. So that's a random excuse to bring those two things together. So density slows light, but speeds up sound. Yes. So it's because one of a wave in matter, but light is a wave in something else. Yeah. So light is an electromagnetic wave. This doesn't permeate, can't travel so freely through objects. However, a sound wave is a pressure wave. The way I like to think about sound waves is, imagine you have a line of dominoes, right? And you push on one side and the dominoes are going to start falling. The closer the dominoes are together, the more likely it is that you're going to get this reaction. If there's a big gap between the individual dominoes, it's going to be difficult for the chain to pass across. So this is what a pressure wave is. It vibrates one atom and then vibrates the next one and vibrates the next one. So if there's a bigger distance between things, then it's hard for sound to travel because it can't pass from one thing to the next. The next object is too far away. But when the atoms are very close together or very compact, sound can travel more easily because it's easier to vibrate the next thing and the next thing and the next thing. So that's why when you have dense objects, sound travels easier, depending on the object, of course, but it is easier to travel through things like that because you can affect the next pressure wave. And this is also why in the vacuum of space, sound doesn't travel, because there's not enough atoms close by for it to pass the pressure wave on to the next thing. It can't create this shockwave type effect. So why nobody can hear you scream in space, because there's not enough things. So anytime you're watching Star Wars and all the ships are doing pew, 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 that is wrong. The ships should be silent. If they're shooting in space, they should be silent. I know it's more dramatic if you hear the explosions, if you hear the pew, 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 but it's not accurate. Space is insanely silent. You should not have lasers making pew, pew, pew noise. Also, lasers don't make noise in the first place. But anyway, let's not get into that. Right now, these are the 3 minutes that T is creating lithium, helium, and deuterium. Yeah, I should measure the amount of lithium in my T to see if I find the missing lithium from the universe. You had 7 minutes for the CMB? Yeah, I had to bring it up. It had been way too long. I just found a random reason to bring up CMB. I see some things. As a general rule, if a comment starts with somebody else's name, I'm just going to ignore it. So if CMB is oldest light in universe, radio waves comes from an earlier universe than CMB light. Excellent question. No. I know based on what I said, that's a very reasonable thing to think, but it also depends on when things are created. Now, the CMB is the afterglow of the Big Bang itself. The photons that were created a few minutes after the Big Bang, these are the ones that make up the CMB. Now, when we use radio waves, we're usually looking at things that have happened after the release of the CMB. So they're produced at a different frequency. They've had different amount of time to travel throughout the universe. If we look at the map of the schematic thing we always use to show the history of the universe, you can see in the middle, we have this recombination thing, this slice of CMB, 380,000 years after the Big Bang. This is when the CMB is released. It's when these photons start traveling freely, but these photons were produced in the early universe when particles form. When we're using radio waves, what we're usually looking at is stuff that has happened between recombination and when the first stars and galaxies turned on, and kind of this big period known as the Dark Ages. Because in this time, there's a lot of events taking place that would release photons, and these photons have then had a different amount of time to adjust their wavelength, but they are created at different energies. So even we can't just use redshift as like how much something has shifted. We also need to take into account what created it and how it was created. Now, the reason that radio waves are very useful is there's a certain transition that happens. So if you consider a standard hydrogen atom where you have a proton and an electron, this electron is going to be in what we call a specific energy level. I'm getting into quantum physics now. There is a simplified picture of a proton and an electron in a circle around it. This is wrong, but it is a simplified picture. There are different energy levels. In a hydrogen atom, the electron is going to be in the lowest energy level. I was not prepared to talk about this now, and now we're going for it. So we're into quantum physics now. So there are these different energy levels where an electron can live. And usually the electrons will start filling out the lower energy levels first, and then gradually the next level and the next level and the next level. It's like if you have a staircase and you start filling up the bottom stair and then the next one and then the next one, and people go up to the next one. So a hydrogen atom only has one electron. It's going to be in the lowest energy state. If you have a bigger atom like lead, you're going to have a lot of electrons, and each one has a different energy state. And there's a nice way of calculating which energy states and how many electrons go in each energy state. There was a rhyme I knew at some point about penguins not flying. It's gone from my mind. It was like stupid penguins don't fly, because the sequence is like SPDF. It makes no sense to anyone. That's fine. Just a random thing that when you're learning about energy levels, there's a specific sequence, and the mnemonic is stupid penguins don't fly, or at least mine was. So yeah, hydrogen atoms. So in the hydrogen atom, you have the proton and you have the electron in the first energy level. Cool thing is, it's kind of everywhere within this energy level. It's not in one specific place. So it's like a proton with a cloud that is one electron around it. Now, the reason I'm talking about this is because this electron can be excited and jump up an energy level and then fall down an energy level again, because it gets excited and it's like, okay, I'm going to calm down now. And it falls down an energy level. And when this happens, this falling down, this extra energy needs to go somewhere. So it actually releases a photon, a particle of light. So if an electron drops down an energy level, it can release a particle of light, a photon. This is something that we can calculate the frequency of the photon that is emitted. And this is something that happens within the Dark Ages, or the so-called Dark Ages, or in that general phase. And it happens that this jumping of, so the photon released by the electron jumping between energy levels is at what we call 21 centimeter. So there's a specific wavelength that it has, that by the time it reaches us today, it should be at a specific frequency, a specific wavelength. And this is something that we can measure with radio telescopes. So that was a lot that I just dumped on you there. And don't worry if you didn't understand it. It's quantum physics. You know, this is part of what we showed in the students in quantum physics, introduction to quantum physics. So this is university grade physics. But you have these atoms, you have electrons jumping in different energy levels. When they do this, they can emit photons. These photons, particles of light, carry a specific wavelength and a specific frequency. which puts them in the radio range. Depending how this happens, we either talk about a Lyman alpha transition, Balmer transitions, or 21 centimeter physics. They're all different properties of electrons jumping about energy levels. But the 21 centimeter one falls in the radio range. So the question that prompted this was about the difference between CMB photons and radio waves, and it's a valid question because if I go back to my electromagnetic spectrum, which is not this image, it's the next one, gamma rays have very high energy, small wavelength, radio waves have lower energy, bigger wavelength, but we can see that something that is currently microwave traveling through the universe eventually will shift into radio. But the radio waves that we measure today are not coming from objects that have already shifted into that range, but not necessarily. It's objects that might have been, so photons produced after the time of CMB, but that due to this specific transition or jumping between energy levels at the quantum level, will have the right wavelengths today to fall in the radio range. Whew. And this is actually really cool because this is a direct way that we can relate quantum physics to my work. So yeah, we can directly relate the properties of these electrons jumping from energy levels to observations that we do in the universe. And here's a really cool thing. You can use things like Lyman alpha data to study dark matter, leaving that as an open thing. I did a video on that, actually. Need to drink my tea before it gets way too cold. It's already borderline cold. Okay, so I know I just dumped a lot of stuff on you about quantum physics. That was a lot of information, but it's really cool. And I actually managed to dump all of this on the students as well. I asked them one day, do you want to know about how we use, because they were studying hydrogen atoms. And I was like, do you want to know how to use hydrogen atoms to measure dark matter? And of course the students said yes. And I was like, haha, you're in for a long lecture now. And I talked for a long time about Lyman alpha stuff and 21 centimeter. It was great fun. Yeah, do not give me free rein to talk about this because I will talk. Okay, comment from Abyss. You hated statistical mechanics. 3 questions and final exam took me about 5 hours. Yeah, statistical mechanics is complicated and difficult, and there's a lot going on. And I took that subject in German. I did that as part of my exchange program in Vienna, and I took thermodynamics and statistical mechanics in German, which just made the whole thing even crazier. But it was a super fun topic. But also one that I understand people not liking so much. We should chip in for an Ember tea mug, maintains temperature at all times. Yeah, but then it would be too hot unless I can set the temperature. If I could set the temperature, like reach like 42 degrees and then stop cooling down, that would be perfect. Yeah, I need one of those heat pads that will keep my tea warm but not hot. I should absolutely get one and branded, like cup of Cosmology heat pack, a cup the cup. Yes. Oh, anyway, comment here. Yeah, I'm ignoring the comment about lithium there. Okay, so I hope I didn't lose anyone with just randomly dumping quantum physics on you. If I'd known that I was going to go down that path, I would have prepared pretty diagrams to go along with it, but that was just a random topic that came up. So sorry about that. If it was confusing, please feel free to ask questions, as always. And on that note, if you don't understand something that I said during outreach, that is on me. It is not on you. Yeah, I have a lot of opinions about how science outreach should be done and how it should not be done. And a lot of people seem to think that being an arrogant, condescending prick is the way to do outreach. Yeah, anyway, moving on from that, there was a comment that I did want to get to by Abyss. How is the optimism around detecting cosmic neutrino background with upgrades to Dune, Super Kamiokande, and other neutrino detectors? Okay, something Maxwell, something. Yeah, it wasn't Maxwell who I was thinking of there, but yeah. Anyway, a lot of people are bad at science outreach, in my opinion. But in the same way that we have the cosmic microwave background, we have this amazing background image. Not that I had the image ready, but I do have the image ready. So in addition to the cosmic microwave background, there could be something similar known as the cosmic neutrino background. And if I go back to my history of the universe, we see that the CMB was produced 380,000 years after the Big Bang. But a lot before that, at the time when matter and antimatter annihilate not long after that, around when the universe was like 1 MeV, which is still within the first 3 minutes. So within the first 3 minutes of the universe, there are a lot of neutrinos, and the neutrinos are also going to break away. In the same way that later on photons break away and make up the CMB, at some point neutrinos broke away. And these neutrinos make up today. Maxwell was in regards to fancy mug. Yes, yes. Good. Yes, I could get a Maxwell mug. Yes. Get a Faraday cage for my mug. Not that it would be in any way useful. I just like Faraday cages. In the same way, we have the cosmic microwave background radiation 3 minutes or so after the Big Bang, or after inflation, like about a minute after the end of inflation, all of the neutrinos that were around in the early universe can also break away and decouple. This means there could be a cosmic neutrino background out there, and this is very, very likely. We expect this to be the case. Now, the problem with neutrinos are a particle in the standard model of particle physics that travels at almost the speed of light and is ridiculously light. It has barely any mass, but it does have mass, and it doesn't travel quite at the speed of light. Those two things are connected. And if you travel at the speed of light, you can't have mass. You can only travel at the speed of light if you're massless. People used to think neutrinos were massless. Then we found that neutrinos actually have mass and therefore do not travel at the speed of light. Now, the problem with neutrinos is they only interact via the weak force and gravitational force. It means they don't interact via the electromagnetic force, which does mean they sound a lot like dark matter, but we know neutrinos can't be all of the dark matter, or galaxies wouldn't look the way they do. I think we've had 3 CMBs today, right? Did I only show it twice? I thought I showed it 3 times, maybe only twice. Yes, anyway, CMB is a regular appearance. Technically, the CMB is the very first thing you see because the CMB is in the Cup of Cosmology logo. So already when the loading screen is up, you should already be seeing the CMB. So technically, the CMB is the very first thing that appears. Okay, so I see there's a lot of discussion there about the best temperature to drink a tea, and that can very easily distract me. So I'm trying to ignore those comments, but keep on discussing because it's really fun. I go back afterwards and read your discussions, and it's always really fun. So neutrinos can't be dark matter, or else we wouldn't have galaxies. They travel almost at the speed of light. They have no mass. They are ridiculous. They have very small mass, almost the speed of light. They are ridiculously difficult to measure. So we know that this cosmic neutrino background is out there, but we have not been able to measure it yet because neutrinos are extremely difficult to measure. But this neutrino background is so overwhelmingly large that if you hold up your thumb, every second, 60 billion of these cosmic neutrinos are zipping through the tip of your thumb. If we can ever measure these, it would allow us to get a snapshot of what the universe looked like less than 3 minutes after the end of inflation. So CMB already gives us an amazing amount of information at 380,000 years after the end of inflation. But if we could get the cosmic neutrino background produced like a minute after the end of inflation, or in the first seconds after the end of inflation, it would be incredible. We have not been able to detect it yet because it's really, really small and difficult to measure. Not small, it's just very hard to measure because it doesn't interact. So the question that we had here somewhere, I lost the question. Was it really that far back? Yes. Before the statistical mechanics on. Okay, so can we measure this with upgrades to Dune, Super Kamiokande, and other detectors? I think no. I don't think Dune or Super Kamiokande will ever have the sensitivity to measure the cosmic neutrino background. That's not their mission. They're measuring neutrinos produced in the sun and in different things like this that are higher energies and therefore easier to measure. If we think these neutrinos have been traveling for quite a long time, their energy is going to be much lower. However, there is a planned mission, the Ptolemy detector, which is hoping to measure precisely this, the cosmic neutrino background. It's still in the planning phase, I believe, but it's a mission that would be specifically looking for this background. I don't think any of the existing experiments, Dune or Super Kamiokande, I don't think these would, or the SNO, I don't think these would have the sensitivity to measure the cosmic neutrino background, but there are plans in the future to launch a mission specifically designed to measure this, which is kind of cool. And I really hope we get that someday. It would be amazing. But more than that, I hope we get our gravitational wave mission in the next 15, 20 years. LICE is going to launch. That will also give us an amazing, amazing, amazing amount of information. So Neutrinos are out there, we're going to find them someday, but I don't think we currently have any experiment that is ready to find them. So I don't think June or Super Kamiokande would be able to do that anytime soon. Okay, it's not the CMB slide, that is true, I know. The one in the logo is the CMB, but it is not the CMB slide, the one you all are waiting to see. This one has to make an appearance at least once in every stream, and yes, it always does appear. There you got another flash of the CMB, because why not? I finally have a Quark board on my office. I requested one ages ago, and I finally have a board where I can pin stuff above my desk. And the very first thing that went on that board was the CMB hologram image that I have. That depending where you look at it from, you cycle through all the CMB maps that we have, like from WMAP to Kobe WMAP and Planck. And the way I've positioned it, I'm sat at my desk and I look up and I see the Planck CMB right above me in my office. I love it. My board has a bunch of random stuff on it, but the first thing that went up was the CMB. I wonder how that's going to go. 1 neutrino pixel in 10 years. Yeah. It's going to take a while, but I do hope that someday we will actually get measurements of the cosmic neutrino background, because that would be really, really, really cool to have. Someday, maybe. I'm optimistic. So there was actually one thing I did want to talk about very briefly, and I got through all the questions, I think. So a couple of days ago, there was the exciting thing in the news of asteroid passing close to Earth within the distance of satellites. A quark board, yes, not a quark board. It's a quark board. I can like pin stuff up on it. It's very pretty. It's actually not even real quark. It's a fabric that I can just pin stuff on, and I love it. I've been waiting for it for ages, and they finally put it up on Tuesday. I was very happy. So a couple of days ago, there was the news of asteroid going to pass close by to Earth. Close by, relatively speaking, it was closer than some satellites, which is cool. What is even cooler is that we only kind of learned about this like 3 days or a week before it happened. And that's always fun, because anytime there's an asteroid, it's fun. So we're pretty sure there's not an asteroid about to hit us anytime soon. And usually when you see a headline of asteroid passing close to Earth, no, it's not going to hit us. No, it's not. If you see the hyped up stories of, is an asteroid going to hit us? No, the answer is always no. And if it were, the headline would be asteroid heading for Earth, and then people would ignore it. But if it's phrased as, is an asteroid going to hit us? Answer is no. But there was this asteroid, and it's very cool because it's a reminder that there are a lot of space rocks out there that we haven't found. Now, the one a couple of days ago was only about 5 meters big, which means if it were on a collision course with Earth, it would burn up in the atmosphere. There would be nothing bad with it. But there are a lot of asteroids out there that could be more damaging. There's actually the thing of like, how big does an asteroid need to be a catastrophic event, right? You can think the asteroid that passed close by the other day was about 5 meters. There's a lot of them around the universe. There's a lot of them around. We don't know where most of them are because they're kind of small, but we don't need to worry about that. Ones we need to start thinking about are ones that are like 25 meters big. Ones that are about 25 meters big are going to hit the Earth on average once every 100 years. There's probably about 5 million of these close to the Earth. About 5 million, close-ish. There's probably about 5 million of these 25-meter asteroids in the sky, in the universe, in the solar system. Once every 100 years, one is going to hit the Earth. However, it could cause minor injuries, but we don't expect it to be dramatic. Would be an explosion in the sky, would probably destroy a few windows, some minor injuries. Now, the worrying thing is that we've only found about 0.5% of these. So out of 5 million, we found a very small fraction, less than 1%. But these are not overly life-ending, threatening events. Then we can scale up. Let's go to the big scale, and then I'm going to work my way down. The ones that are like mass extinction level event, kind of like the one that wiped out the dinosaurs. Here we're talking about an asteroid that is several kilometers big. And these are ones that would create a mass extinction event. They would like wipe out life as we know it. We expect that one of these is going to hit the Earth every about 100 million to 200 million years. as the opening of that very, very scientifically inaccurate film Armageddon says, it happened before, we know it's going to happen again, it's just a matter of when. That is true. But these are very big rocks, they're easier to find. There are only 4 such rocks that we found around the Earth, and we found all 4 of them. We don't expect there to be more. These are big, they're easier to find. If there were a mass extinction causing asteroid, it's quite likely that we would see it and have some warning. Not that we could do much about it, but at least we would have some warning. Asteroids that are about 1 kilometer across, we expect about 900 of them within near Earth area, kind of like the solar system. We found 95% of them. These would be global devastating events. It would create like a 10-kilometer crater. We expect one of these to hit the Earth every 500,000 years. Now, the ones that are a bit more worrying, the ones that we do need to worry about a bit, are the ones that are about 150 to 200 meters. We expect that one of these, about a couple 100-meter asteroids, one of these should hit the Earth every 20,000 years. This would produce a 2-kilometer crater, 1 or 2 kilometer crater, would probably kill a lot of people, but wouldn't be a extinction level event. It would just cause mass casualties. Now, we expect there's about 25,000 of these within the solar system. We found about 35% of these. So these are the ones that, someday could be problematic because there's a bunch of them that we haven't found. But again, this is only going to hit the Earth once every 20,000 years. So they're not regularly occurring events. The thing about space is very, very big and very, very empty. There's a lot of rocks out there, but there's also a lot of empty space between us and all the rocks. So it's not overly likely that an asteroid is going to hit us. The most dangerous ones we would definitely see coming. The ones that are medium size, medium danger level, those are the ones that are probably the most problematic because those are the hardest. But in any case, even this one, that is a 5-meter rock, it's kind of small. We were still able to find it with a few days' notice. Not really enough time to actually do anything. But the bigger the asteroid, the more potential damage it could do, but also the greater the chance that we see it coming and can do something about it. As people are saying here in the comments, we could be surprised, much like with the Neowise comment. Yeah, there's always going to be stuff that is pretty in the night sky that suddenly happens that we didn't see coming. But it's very, 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 very rare that something would be headed on a collision course to Earth. So anytime you see a headline of, is an asteroid going to hit us? No, it's not. But it is a nice reminder that there are a lot of space rocks out there, and eventually some are going to hit the Earth, and we just hope it doesn't happen soon. Now, of course, if we see it coming, we could try to enact some kind of strategy to prevent it crashing towards us. We very much should not take a bunch of Bruce Willis people and company off of a drill site and teach them how to be astronauts. I think teaching astronauts to drill would be much more reasonable. But anyway, there are strategies we're thinking of. We have things like the DART program, which was a baby mission that was sent to space that crashed into a rock to see if we could move it. There are ideas. So it's not something we need to worry about too much. And I'm throwing out Armageddon references. That is one of the most scientifically inaccurate films. Someday I could do a whole stream just tearing that film apart just for fun. Like, here's everything that the film gets wrong about science, and let's not even focus on the plot holes. If anyone's up for that, I could do that one day. It's a great film. It's a laugh. It's one that you put on and don't have to think about, because when you start thinking about it, the whole film falls apart. It's a laugh. And if anyone wants me to do an episode of Cup of Cosmology, let's talk about what's wrong in a bunch of movies, we can do that. Could do Interstellar as well. The issue with asteroids isn't just size, in my opinion, if the impact knocks out key infrastructure such as power grid or agriculture hub. Yeah, so it always depends where it's going to hit. Now, statistically, it's more likely to hit in the ocean just because the Earth is 75% covered with oceans. So statistically, any asteroid is likely to fall in water, but if it lands on land, then it could be much more problematic. Medium one is waiting for you to buy a new house. Yeah, house insurance usually don't cover asteroid damages. So yeah, just check there's no asteroids coming before you sign the house. So people seem keen on me tearing apart Armageddon from a scientific perspective, but Bruce Willis, I agree, but also science, and you could do a scientifically accurate Bruce Willis film, but I guess that wouldn't make sense because once you bring Bruce Willis in, it's just explosions and chaos, and Yeah, and then you throw reason out of the window, or out of the window. Yeah, literally out of the window if it's Bruce Willis, always throwing stuff out. Anyway, yes. On the comment that Abyss just made, asteroids could knock out key infrastructure. There is a very cool thing that there could at some point be a random event that could just knock out power to all of Europe for 2 weeks, and we are so not prepared for this. Like, there are key infrastructures in the European grid that could be taken offline accidentally, not accidentally, but could be damaged somehow. There could be a European-wide blackout. We don't think it's likely, but it's something that is good to be aware of that could happen because nobody is prepared for that. Like, what would you do if you suddenly had no electricity for 2 weeks? You know, and it goes beyond just, okay, I won't be able to charge my phone, no internet. It's like, how would you heat up your place? How would you have food? Do you have enough food to last 2 weeks? Anyway, let's not get into potential apocalyptic scenarios, but that's just something to bear in mind. This is why we need an asteroid laser defense grid that can pew, pew, pew. Yeah, set up lasers, add sound effects to the lasers just because why not? We like sound effects on our lasers. Okay, so a lot of tangents today. We talked a lot about tea and the right tea temperature for tea. A lot of tangents, been talking for more than an hour, so it is time to wrap up the stream. NASA claims that there are 108 inaccuracies in the movie Armageddon. We should dedicate a session to find them all. Yeah, I think for copyright reasons, I'm not allowed to play the film on Restream while we tear it apart. But what I could also do is do a kind of watch Armageddon and live tweet it as I go. So we could do that. We could do a watch party at some point. We will watch Armageddon together and live tweet all of the inaccuracies that we find. Come up with inaccurate Armageddon, some fun hashtag, and we all tweet out the inaccuracies that we find in Armageddon. It could be a laugh. Maybe someday I should set that up. And if it works, it could be a recurring thing, like Cup of Cosmology tackles sci-fi films. Could get out of hand very quickly. We had laser sounds like we had smells to gas. Yes, it's just a warning, right? Although if you hear the laser, it's already hit you. Light travels faster than speed, unless of course you're traveling through a neutron star, as we saw today. So maybe having lasers make sound makes sense in a neutron star, because then you can get out of the way before it hits you. Deep Impact is also a good asteroid movie. Deep Impact is more scientifically accurate than Armageddon, and I like the ending of it. It's still kind of a bit flaky in terms of accuracy. Speaking of inaccurate sci-fi films, one of the most absurd, scientifically, cup of inaccuracy, I like that. One of the most absurd films that claims to have science in it is The Core, with the premise of the Earth's core has stopped spinning. We're going to drill into the center of the Earth, drop a series of nuclear reactors, nuclear bombs, to restart the core of the Earth. It is just the whole premise of the film is so bizarre. Yeah, you watch that film and just the whole thing's like, what, why, how? It's almost as bad as Magnetic Tornado film, where they have a tornado of magnetic field that is wreaking havoc in the US. Yes, there's a lot of very inaccurate films. But on the note of the Earth's core has stopped spinning, just a general comment, no, it hasn't. There were some popular science articles in Spanish media the last week that were saying scientists have found that the Earth's core is slowing down, catastrophe incoming, like thing. And just from the headlines, like, no. Yeah, I haven't attempted Moonfall. I know it's so bad. So, yeah, if you've seen stories recently saying scientists worried about Earth's core slowing down, no. There's some scientific simulations going on that show that this is a thing that might happen. It's not something that is happening now. It's not something that you need to be concerned about. So yeah, there was a lot of hype of like, Earth's core, stop spinning. No, there's a general rule that we use in scientific publishing that also applies to a lot of popular science things. So in science publishing, if an article has a question in the title, the answer is no. Like sometimes you see a paper with the question of, have we found dark matter? No. Does dark matter do this? No. Do gravitational waves? No. If there's a question in the title of the paper, the answer is no. Really. It's just like 99% times it works. There was actually one for paper where the abstract, like summary of the paper was just the word no to the question they'd asked in the title. It was really funny. But usually this is true for popular science, sensational headlines and pop sci articles as well. If you see a headline like, is an asteroid going to hit the Earth? Has the Earth's course stopped spinning? Are we on a collision course with something? The answer is always no. It's hype. The day it's yes, they will lead with that. You only ask it as a question if you're trying to gain interest. Otherwise, you state it as a fact. Anyway, putting that rant aside. Cool. An hour and 10 minutes in today, getting onto the topic of bad sci-fi films at the end of the stream is a bad idea because this is how I can keep the stream going for way too long. Hollywood needs to hire me as a science advisor. That would be really cool. I'd be up for that if Hollywood wants to get in touch. Contact thatcupofcosmology.com. That's where all of you can contact me. As always, you won't believe this one simple thing you can do to find dark matter. Yeah, one simple thing. Spend years and years looking. Good luck. One simple trick. Life hack. Do science rigorously and maybe one day you'll get the good results. Or fun results. Okay, so that's called Betteridge's law when it happens in journalism. If the headline asks a yes/no question, the answer is almost always no. Yes. Yes, the answer is almost always no. I think in general it's a good approach. If someone's asking a sensational question, the answer is no. You can. Okay, before I go off on another tangent, thank you everyone for joining today. This has been great fun. We've had some really cool comments. I have not watched For All of Mankind. I really wish they'd just called it For All of Humankind because there's no reason to call it mankind when the word humankind is right there. Anyway, I haven't watched it yet. I've heard that it's very good, so it is on my watch list at some point. But currently, I'm just rewatching Sense8, so I'll get there eventually. Okay, thank you everyone for joining. We've had some really, really cool questions today, a lot of random tangents. Most of the random tangents were me going off on random tangents. Always fun. So, Cup of Cosmology will be back next Sunday, same time as always, at 7 p.m. Central European Time, 1 p.m. if you're on the East Coast, 10 a.m. if you're on the West Coast of the US. There is a time zone converter on cupofcosmology.com. As always, if you want to request a topic, if you want to chat to me, if you want to send me messages, all the details are on cupofcosmology.com, and you can email me or reach out on Twitter, although I'm not actually on Twitter much these days. I have shifted completely to Mastodon and not going to go there. Yes, I am now happy on Mastodon for all Homo sapiens. Yes. Come to think of it, when they should have gone for all humanity. Yes, it's just easier. Hopefully you might go off on a sine or cosine sometimes. Yeah, I always go on tangents. I never go on sines or cosines. That would be fun. Then you can just bounce about like a wave. Okay, thank you everyone for joining. This has been great fun. Cup of Cosmology will be back next Sunday, and then I'll be taking a break for a couple of weeks because I'll be traveling, and then we'll be back with a special creativity and relativity, whatever random stream we're doing. Where's your Mastodon? It's linked to in my Twitter. I'm on the tech.lgbtq server, sorry, tech.lgbt server, and my username is dchooper91, the same as on every social media. It's pinned on my Twitter, so you can find me on Mastodon. Okay, thank you everyone for joining. This has been really, really fun. I hope to see you all again next Sunday, same time as today. And I hope in the meantime, you all stay safe and take care of each other.